This presentation is using C+ 2024.3. Dr. Gerard Borello. www.interac.fr. Its topic is detailing SEA and double glazing modeling. Double-walled glazing can be efficiently modeled by SEA. Nevertheless, it is a multi-path system and a minimum of know-how is required for choosing appropriate SEA subsystems. Inadequate choice may lead to inaccurate modeling. In this presentation, the predicted sound transmission losses from various C+ models are compared to available test results from window manufacturer for validity assessment. Analytical C+ calculations of critical SEA parameters are also checked against deterministic FEM modeling in using virtual SEA, VSEA, or reciprocal radiation integral, RRI, methods. Latter method may bypass intrinsic limitations of analytical calculation at low frequencies when loss of accuracy is involved. Hereafter are reviewed. In a first step, choice of SEA subsystems and related poor results if inadequate. In a second step, best C+ practice in building double glazing SEA model. In a third step, sensitivity analysis to changes in system design. The physics of double glazing introduces different acoustic and vibrational paths. Each path contributes to the sound field in the receiver cavity. Thanks to C+ post-processing functions, paths can be ranked in order to guide parametric changes. About double glazing construction. Double glazing improves both thermal and acoustic transmissions. A classical construction for windows is two glass layers of different thickness separated by an air gap. Shown examples share following physical parameters. Glass elastic stiffness is about 71 gigapascal. Mass density is 2,500 kg per meter cube. Air gap thickness is 12 mm filled by air at 1 bar. Dissipation properties are assumed default values when unknown. 1% DLF in structures. 1% absorption in air gap. Double glazing vibrational paths. Two main paths are airborne, emitter window to air gap to window receiver. Structure-borne, emitter window to window receiver through mechanical link at boundary. Emitter acoustic field, the load. Assumed diffuse, random incidences. Loads the first window and inject power in the glazing. Airborne subpaths transmission. As mass law through window non-resonant modes radiation in receiver. As modal radiation of structural vibration induced by acoustic. Structure-borne subpaths. As left window modal energy mechanical coupling to modal energy of right window radiating in receiver. Several mechanical couplings may be added depending on construction. Each path is related to a power flow from emitter to receiver. Each subsystem loses energy through its internal viscous forces represented by their modal DLF in windows. By its acoustic absorption in air gap. Aim of SEA model is quantifying and linking all paths from basic material properties and geometry to compute total transmitted power in receiver fluid. Now a few words about rules for splitting into subsystems. Substructuration from band integrated random response. At least one mode per frequency band is required for SEA calculation in a subsystem to be reliable. Band without modes are under interpolation, so less reliable levels on outputs. Interpolation can be set to modal, non-resonant vibration when no mode, or to statistical, envelope of modal responses with interpolation when null mode in band. Substructuration from geometry. In the estimated direction of propagation, the related size of the subsystem must be at least half of a wavelength of the supported vibration at the lowest required eigenfrequency. In the normal direction, air gap cannot be considered as a subsystem below 12 to 14 kHz. The metallic frame attaching windows cannot be considered as a subsystem as its width is around 26 mm. Modeling the frame as a plate of length 1.48 m by 26 mm width under simply supported edges provides left top modes in band graph. Frame is then not a subsystem below 4 to 8 kHz. Reliable frequency range from modes in band starts from 80 Hz in 1/3 octave band. Please note that our reference test measurement stops at 5 kHz. Double glazing has also to be modeled using only two flex Ural plate subsystems, the windows. Conclusions about outcome from unsuitable partition. Newcomers to SEA will tend to split the glazing into three independent subsystems as there are presence of air gap modes down to 125 Hz. The splitting decomposes the system into glass 4 as flex Ural plate, air gap 12 as cavity, glass 10 as flex Ural plate. Emitter cavity and receiver cavity are modeled as diffuse field cavity. As below 14 kHz air gap modes are tangential, 1D and 2D modes, without oscillation in the thickness and behaving as static in that direction while involving stiffness coupling between structural window layers. From this, there is no air gap resonant oscillation along Z direction and air gap cannot be considered as an SEA subsystem for frequencies lower than 12 to 14 kHz. Keeping this choice, way to cross-couple retained subsystems has also to be chosen. In SEA, subsystem modes with a frequency analysis band are exchanging energy when coupled so that emitter cavity has to be coupled to glass 4 to air gap to glass 10 to receiver cavity. This is sketch A model. Thin flat plate inserted between two SEA cavities generates additional non-resonant energy transmission that does not flow through resonant modes. This energy flow depends only on mass density of the plate, leading to so-called mass law transmission. The mass law energy exchange may be simulated in SEA by an indirect coupling between the modes of the two cavities coupled to the plate as done in sketch B. Last, a mechanical coupling is introduced between glazings, model C. This is the most intuitive SEA partition, but for double glazing, it has severe limitations. Next slide. This model is implemented, solved, and predicted acoustic transmission loss compared to experimental data. Synthesis of TL outcomes from A, B, C models against TL test. For quick check, the measured TL is imported in the emitter-receiver junction. Consequently, A, B and C predicted pressures in receiver can be compared to pressure retrieved using measured test transmission loss. One observes that none of these models are able to retrieve test expected pressure within a decent confidence level. Model C is the less dispersed as it introduces the mechanical coupling between windows, which is expected to be the predominant path at high frequency, but we can't consider A, B and C models are predictive. The retained conclusion is that not observing substructuration rules leads to biased results. Transfer matrix method combined with SEA for modeling double glazing. 3 TMM matrices applied to SEA. Both plates and cavities are required to capture the various airborne and structural paths. To each subsystem are allocated faces, in cavities, or zone, in structures. Their areas are all set to window size equal to length times width. Normal to plate is always pointing to external cavities. Automatic double wall creation in C+ 2024.3. Due to the number of paths and trims to introduce in double glazing TMM solution, the construction is automated from required elementary set of input data. Area and section of walls. Intermediate trim to insert between the two walls. Geometry and fluid of emitter and receiver cavities. C+ mechanism of TMM trims and SEA subsystems hybridization. Inelastic 3-layered trim is inserted in emitter-receiver junction. 2 layered trims are applied to plate faces to attenuate their radiation and their received pressure. Each path can be analyzed separately from others, models E, F, D in demo. Test TL against TL predictions from D, E, and F models. TMM provides a good physical prediction of SPL in receiver for all models D, E, F up to 2 kHz, and adding mechanical links, E, F, provides better match with test SPL up to 5 kHz, test limit. Let us quote that high frequency SPL cannot be predicted without mechanical link simulation, D. An observed offset of around 2 to 3 dB between test and predicted SPLs is found in these models between 200 to 1600 Hz. In the latter frequency range, the acoustic path is entirely driven by the total transfer matrix inserted between receiver and emitter. The observed 3 dB difference with test is explained by the finite size of the actual glazings that induces modal selectivity around first breathing frequencies of the assembly. The air gap drives this selectivity, though its acoustic static stiffness in the finite system, while TMM calculation is on its side, assumes infinite-sized coupled systems with no modal selectivity. When the system is finite, only 2D tangential acoustic modes are supporting the air gap vibration. Therefore, the static pressure due to acoustic stiffness is only driven by volume variation of structural modes. Only odd-order structural modes induces air gap volume variation. Consequently, half of the total number of structural modes, both odd and even, that is half of the total vibrational energy, participate to the transmission. An extra attenuation as 0.5 constant transfer is, therefore, inserted in the emitter-receiver junction for correcting infinite TMM calculation when the breathing frequency path is dominating. Final retained model, F, for double glazing transmission. This model includes mechanical coupling between windows as required to explain the test result for frequencies lower than 5 kHz. Observed offset of around 2 dB of RMS SPL between 200 Hz to 1600 Hz, explained by selectivity of excited structural modes in the finite system, leads to a 0.5 correction of the non-resonant coupling between emitter and receiver cavities. In this frequency range, the acoustic path is entirely driven by this path. Mechanical CLF between the two plates fit with continuity of rotation and translation at plate boundaries in corresponding FEM model, simulated by a line junction in C+ double wall model. Verification of line junction analytical computation is shown in next slide thanks to FEM modeling and VSEA. Designing line junction between windows. C+ line junction assumes continuity of rotation and translation at boundary, and it may be simulated by two repetitive junctions, one for x-axis boundary and another one for y-axis boundary. In FEM, the equivalent modeling is generated by distributed RBE2 connections at boundary. Going further with virtual SEA, VSEA. The exact type of mechanical coupling between the two glass sheets is not coming with the test result, and our previous model was inferring it, assuming an SEA line coupling connection between the two sheets. Built-in C+ analytic solver provides order of magnitude of connection strength, described in C by 2 CLF spectra, the coupling loss factors. In C+, more deterministic SEA parameter, and in particular CLF, is provided by virtual C post-processing called VSEA method. FEM provides on-output series of mode shape amplitudes at a set of user-selected reference nodes that are the inputs of VSEA solver in C+ user interface that will compute equivalent C CLF. Reference nodes are spread around on each of the two glass sheets. The VSEA model is built automatically from the reference modal amplitudes, and from a partition into groups of nodes, bijective to subsystem partition. Hereafter we may look at the selected FEM model of the window coupling. VSEA model of line junction compared to C+ line junction. Agreement between C+ analytical CLF and FEM-derived CLF, through VSEA, is excellent from 100 Hz. Note that analytical CLF of the two parallel ASEA junctions are summed up, as VSEA only delivers the total CLF of the coupling perimeter. RRI check of structural path. C+ RRI method, reciprocal radiation integral, is now applied to check the emitter glass 4 glass 10 receiver path, structure-borne path, in a corresponding FEM model without air between the windows. From previous FEM, all modal amplitudes on glass 4 and glass 10 surfaces are exported in two different Nastran OP2 files. From the two OP2 files, two RRI objects are created in C+, and combining both, the transmission loss coefficient is computed by RRI using 1% DLF. We can verify in here below graph that the RRI TL is shared nearly equally into resonant and non-resonant for 1% DLF. When comparing measured TL with RRI and ASEA TL, RRI and ASEA are found pretty close except in region where acoustic path is dominant. Acoustic path is inducing a breathing resonance between windows with a related decrease of TL in 100 to 500 Hz region. This decrease is clearly visible in the test TL of the retained glazing model. Hybrid C plus TMM TL is given hereafter, computed from F model with line junction between windows with only one tuning, the factor 0.5 added for airborne path mode selectivity. Added mass and DLF from trim options are enabled in Windows subsystems. For frequencies larger than 1 kHz, some distortion is observed between test. For more accuracy, window DLFs need measurements with knowledge on actual mechanism of coupling windows at boundaries, unknown and assumed to be a line junction. Radiation CLF is well predicted at high frequency and is not a source of discrepancy.
Sensitivity to different parameters.
Radiation efficiency, sigma-rad, review. Sigma-rad drives resonant joint acceptance and radiated power. Its influence on TL is tempered at low frequency by the non-resonant flow of energy. HF analytical calculation from C+, numerical spatial windowing and Madonic algorithms, is pretty robust when comparing with RRI/FEM radiation efficiency under same boundary conditions, simply supported on edges. Added mass from trim option is enabled in Windows subsystems and may slightly increase low frequency wave number depending on effective added mass. At low frequencies, sigma-rad depends on boundary conditions and its variability may be analyzed by RRI, setting different boundary conditions in the FEM structural model. Synthesizing results. Hybrid S.E.ATMM model, F, including airborne and structural path simulations, provides the best approximation of measured TL for double glazing system. Added damping to plate by the trim appears as very effective prediction. In conclusions, modeling air gap as a subsystem is not an issue despite there are more than one mode in band count above 100 Hz. What matters is exhibition of resonances in air gap along the main propagation direction, the z-axis, only occurring above 12 kHz. Below, air gap is a flat cavity with only tangential modes. Their velocity, perpendicular to glass plate flexural velocity, leads to weak modal coupling. As a result, air gap mainly acts as compressional stiffness creating a breathing resonance with masses of both windows. For air gap filled by foam, modal selectivity is reduced and double wall models do not need 0.5 correction. Application to triple glazing, argon fill. Plain blue is the reference SPL from F model tagged Air 2. Air 3 is the tag for the triple glazing filled by air, plain red, and argon 3 is Air 3 replaced by argon in air gap and related SPL is dashed blue, argon 2, and dashed red, argon 3. The only benefit of triple glazing compared to F is lower level observed at 25 Hz due to argon and around 1 to 2 kHz due to lower radiation efficiency of outer window, 4 mm, but above larger SPL is observed. TMM theory offers a rather good approximation of the transmission between 100 and 1000 Hz when an extra coefficient of 0.5 is introduced in the non-resonant path coupling emitter and receiver cavities and justified by modal selectivity in the finite-sized system. Application to triple glazing, helium fill. Plain blue is the reference SPL from F model tagged Air 2. Green is for argon 2 fill and helium 2 for helium fill. Left is the acoustic transmission loss in dB, -10 log, prad/pin. Right is the transmission coefficient as P rad over P incident, power radiated in receiver per unit incident power on emitter glazing face. Obviously, helium fill improves quite a lot TL between 100 and 1000 Hz.
Conclusion.
C+ models of sound transmission properties of double glazing captures the physics quite accurately through its internal analytical dynamic operators. The bridge offered by virtual SEA, VSEA, and reciprocal radiation integral, RRI, to convert finite element models into C parameters allows overriding some analytical parameters or, as it was done here, verifying the quality of analytical parameter predictions. This unique feature leads to robust model construction at low cost as it reduces the additional cost of experimental data. In this example, the only measured parameter is the transmission loss, necessary for demonstrating confidence in proposed modeling. Thank you all for attending this presentation. Give your feedback at gerard.borello@interac.fr.